Okay, so in this video, we're going to talk about finding areas underneath a curve, and we're going to talk about approximating the area underneath a curve using a repetitive process of adding up areas of smaller rectangles underneath that curve. So I'm going to sketch it out in a couple of different scenarios and show you that there's different ways that we can actually do this, and then I'm going to show you in an example of how we can kind of put this together. So to find the area underneath a curve, we can approximate this at this point. Let's use rectangles for doing so. Let's consider the area of the region that's bounded by the curve, the x-axis. Where's my curve? There's my x-axis, and then we're going to use x equals a and x equals b. And so we don't know at this point, based upon geometry or based upon any other method, how to find the area of this region in here. And in this first process that I'm going to walk you through, I'm going to call this an upper sum. So I'm actually going to come up with an over approximation of the area of this region. And the way that I'm going to do this is, as I mentioned up above, I'm going to use rectangles. I'm going to say, let's break this up into n subintervals. And so imagine, in this case, it looks like I've got 1, 2, 3, 4, 5, an n of 6 or something like that. But you could have however many you want. And in this case, if we had an n of 6 and I was creating this upper sum, I would do it like this. I would look at that very first region or very first subinterval that I've created, and I would say, what is the largest y value of the function on that subinterval? And you can see that the largest y value occurs on this end, right? The largest y value would occur over there. And that becomes the height of the rectangle that I'm going to find the area of. So my picture here would look like this. So this is how I'm going to get my over approximation. Based upon how this function is shaped, it looks like I'm always using that right endpoint, because isn't that right endpoint always the highest y value on a subinterval? And so you could see that you would end up with so many rectangles, and you could add those up to get an area. I could also show you how to find a lower sum, and a lower sum would be an under approximation. And again, the idea is, let's find the area of n rectangles. So I've got n subintervals. So let's say there's my region, and I've got x equals a, and we're going up to x equals b. And okay, so we've got these regions, and this time if we're going to find a lower sum, I want to look on the first interval and say, okay, well, I'm going to use the lowest y value on that interval as the height of my rectangle. I'm going to use the lowest y value as the height. So you can see in this case that it's actually going to be consistently using the left endpoint of the interval. Like look in this last, or I guess the second to last interval. Isn't the left endpoint going to be the lowest y value on that interval? And so that's what we're using in this case for the height of our rectangle. So you can kind of see that this upper sum in this case, which just happened to also be what I would call a right-hand sum, and this lower sum, which I would happen to call a left-hand sum, you could see that they would give approximations, and there's going to be error. So there's different ways of improving our accuracy, and we're going to talk about how we can actually converge to the exact area in the next video. But a lot of times in math, estimations are good. And sometimes we estimate with upper sums, sometimes we estimate with lower sums, sometimes they are midpoint sums, or sometimes they are left-hand sums or right-hand sums. And even though this one above was a right-hand sum and this one right here was a left-hand sum, it does not always mean that upper sums are going to be right-hand sums and that lower sums are going to be left-hand sums. It was just coincidence based upon how the function was shaped. But the point is, there's all of these different methods for estimating areas, and all we're going to do, in all honesty, is just say, hey, let's use our basic knowledge of finding the area of a rectangle and then break our regions up and just apply that basic knowledge of rectangles over and over again, add up the areas of individual rectangles. So let's look at the example on the next page. I'm actually going to come back in the next video to the notes here, but that were on the bottom of the previous page. But right now we're going to talk about this example. Let's find the area of the region bounded by the root of 1 minus x squared, the x-axis, and the y-axis in the first quadrant. So if you graph y equals the root of 1 minus x squared, you're actually going to see that that's a semicircle. And so the graph looks like this, where it's got a radius, the semicircle would have a radius of 1, so it would actually look something like this. And this would be at -1, this would be at 1, but it says let's find the area of the region bounded by the function, the x-axis is here, the y-axis in the first quadrant. So I want all of this area. So I really don't care so much about that left side. So just to emphasize that, I'm going to get rid of that left side and just focus on this area right here. And it says let's consider both the upper sums and the lower sums with 5 equal subdivisions. And so if we have 5 subdivisions, and this is going from 0 to 1, then take the length of your entire interval and divide by 5. And so the length of, or the width of each subinterval is 1/5. So we'd be at 1/5, 2/5, 3/5, 4/5, and then 5/5, or 1. And so we are going to generate some rectangles. And at first, I want to do an upper sum. So if I'm going to do an upper sum, then that means in this case, let's see, my upper sum is going to be the over approximation. So that means on each subinterval, I want to take the highest y value and use that as the height of my rectangle. So on the second subinterval, the highest y value is actually on the left side, right? On the third subinterval, the highest y value is on that left side. So you can kind of see how I would be sketching this out. And I'm just going to apply some basic areas now. So we've got 5 rectangles. Let's do base times height a bunch of times. And we know that the height is the y value of the function. And our function, f of x, to get any y value, we would always take the x value and just plug it into root of 1 minus x squared. So you could see that the base of that first rectangle is 1/5, or the width of that first rectangle, and the height is actually going to be f of 0, not f of 1/5, because f of 1/5, that'd be a lower height. We wanted to take the highest y value on that interval, and so that would be f of 0. So if you plug 0 into your function, the y value, or the height of that first rectangle, is the root of 1 minus 0, or just, you know, I'm actually going to write it like this. I'm going to say the root of 1 minus 0 squared, because I want you to see the pattern. The second rectangle would be, we'd say 1/5, because that's the base, and the height is going to be f of 1/5. So that would be the root of 1 minus 1/5 squared. And we're going to keep adding here. The third rectangle is going to be a base of 1/5, just base times height, and the height is going to actually be, you can see the height of that third rectangle is based upon the x value of 2/5 going into my function. So it would be the root of 1 minus 2/5 squared. And this is actually going to go on a little bit longer. You've got 1/5 times f of 3/5, and then we have 1/5 times f of 4/5. And so we end up with, whoops, let me erase that. The 1/5 is on the outside. And so if I put 1/5 there, and then we have the root of 1 minus 3/5 squared, and the last one was 1/5 times the root of 1 minus 4/5 squared. And we can condense this down into the following. We could say that this is equal to, this would be equal to 1/5 times the sum of the root of 1 minus I/5 squared, where I is going from 0 to 4. And if you don't see that at first, you see that there's a pattern. And you see that the 1/5 is there each time, and you see that it's always the root of 1 minus some number squared. Notice that number is starting with 0, and then it's 1/5, 2/5, 3/5, 4/5. And so if you plugged in 0 into I/5, you get 0, and then the 1, you know, you go up by 1, you get 1/5, 2/5, 3/5, 4/5. And so this is how we can condense all of this. If you wanted to, you could simply just plug all that into the calculator, get your answer, and I'm totally fine with this. I'm just showing you this to connect it with what we're doing with sigma notation. Okay, so let's plug this into the calculator and make sure that we get an answer. So I'm going to say 1/5, 0.2, and then multiplied by, we're going to do sum. Whoops, that's going to be second stat. Sum is in math. And then we are going to say, let's sum the sequence. And sequence is in ops. And our sequence this time is the square root of 1 minus, and that's going to be x divided by 5 squared. Start is 0, end is 4. Let's paste that in, and oh, I've got an error, and I wonder if the error was because I put the 0.2 in front. So let's delete that 0.2 in front, and then just evaluate this, and then try it again. What is my error? Oh, I see what my error is. I've got the whole thing underneath the square root, so I need to fix that. So let's go back into that list menu, and let's go back to number 5 where we do the sum. Oh boy, I better clear this. Back into number 5 where we do the sum of the sequence. And oh, you know what I need to do? This is actually really good that I made that mistake. I need to go back over here and I need to close this off. So since I did not, let's see, I want x over 5 squared first. And so let me go back a little bit. Let's hit here. I'm going to start over. I'm going to say square root 1 minus parentheses x divided by 5, close parentheses, squared, close parentheses. By not closing those parentheses before, that's why it was including all of that other stuff inside the square root. So make sure that you close those parentheses. I'm actually really glad that I just made that mistake. So we go down, we hit paste, and press enter. Now we don't get an error, but remember, we need to multiply this by 0.2. And when we multiply it by 0.2, we end up getting our final answer that is the correct answer, and that is 0.8593. Okay, so that's my lower sum. Now let's, or I'm sorry, that's my upper sum. Now let's do the lower sum. But I want you to see that if we do a lower sum, the only difference is there's only a subtle difference, because in the lower sum, this first rectangle is not going to be there, but the first rectangle that you would have based upon this first subinterval would actually go here. I'm going to change colors for a second. It would actually go right there, and then you would have one that would go right here, and then you'd have this third one that would be there, then this one right here. So if you look at it, do you see that this rectangle that was the second rectangle from before is now our first rectangle? The rectangle that was our third rectangle from before is now our second. The rectangle, so a lot of these are the exact same values is what I'm saying. And so what's the only difference? Well, I guess the only difference, if you think about it, you know, look at this last interval. Can you see that if you use the lowest y value in that interval, the height of that last rectangle is 0? So with a lower sum, you're actually losing a rectangle entirely. So you only end up with 4 rectangles, and the one that is not repeated that we did have with the upper sum was actually that very first rectangle that had a height of 1. And so the lower sum, if you go through the same process that I just went through with the upper sum, is going to be all of this stuff, but it's not going to have that very first term that we had from before. So our lower sum is actually going to be 0.8593 minus that very first rectangle, which was, it's one that I can evaluate in my head because the square root of 1 is 1 times 0.2, so it's just, you end up with an answer of 0.6593 for that lower sum. And so sometimes you can do this where, you know, when you do the upper sum and the lower sum, there's some overlap, and given the overlap, you might only need to do a little bit of reasoning, and you might not have to go through the entire process again. But hopefully this is a good example that shows you that we can just rely on doing base times height a handful of times. And if we want, we could put it into sigma notation and evaluate, but you don't have to. You could simply do base times height 5 times in this case and get an answer. And you can do it with the upper or with the lower. Okay, in the next video, we're going to talk about how to find the exact area.